Chapter 5, Section 1, the objectives. First, analyze the modern periodic table from the historical perspective, particularly the role played by Mendeleev. Analyze periodic law and periodicity, and identify the significance of SPD and F blocks. So, Dmitri Mendeleev took the first 60 known elements of his time and he put them in order according to atomic mass. So the first way the periodic table was ever organized was in the first way by increasing atomic mass. As you can see, when you go from left to right, the atomic mass gets increasingly larger. Same thing on the next row and the rows to follow. The second way that he organized the periodic table was based on the physical and chemical properties of the elements, particularly their states of matter, color, reactivity, and other properties. He put them in vertical columns or groups based on their properties. So because these are in a vertical group with each other, it means they have similar chemical and physical properties. Same thing with the second group and the third group and so on. The modern periodic table, however, is not organized by increasing mass. It's actually organized now by increasing atomic numbers. So as you go from left to right in a period of the modern periodic table, you'll see that based on the atomic numbers, 19, 20, 21, 22, etc., it's increasing in that way. However, Mendeleev's secondary method of organizing in groups according to their properties still holds true. So the elements in group 1 are all considered to have similar reactivity and similar properties to one another. Same thing like elements in group number 8, for example. These are all called the noble gases. They all are a gas, they all are nonmetals, and they are all non-reactive because they already have what's called a full octet, or they already are stable elements. So because Mendeleev's secondary method of arranging the periodic table still holds true today, it gives him the bragging rights to be considered the father of the periodic table. You might look at it and think that it's still ordered in by the original method by increasing mass. So we have 22.9, 24.30, 26.9, etc. However, at least in one location, there's a discrepancy to that. Cobalt and nickel, cobalt has a mass of 58.933, while nickel has a mass of 58.71, which is less. So there would be one circumstance where organized by atomic mass is no longer the case scenario. Periodic law, the physical and chemical properties of the elements are periodic functions of their atomic numbers, which means that as you go from left to right across the periodic table, there's a specific pattern that emerges, particularly with valence electrons. And that is thanks to the atomic number, because all of these elements based on their atomic number actually gives them each one valence electron, which causes them to have similar properties. Each element in this group, because of the function of their atomic number, they have two valence electrons, which gives them specific properties as well. So when elements are arranged in order of their atomic number, they have similar properties that appear in regular intervals. Periodicity, you should know that horizontally we call them rows or periods, and there are 7 rows or periods. So this is row or period 1, row or period 2, 3, 4, 5, 6, 7. These two down here at the bottom, you'll notice arrows that come up here, actually belong in rows 6 and 7 in this little area in between the S block and the D block. Groups or families are the vertical columns. So if you have elements in this vertical column, we call them a group or a family of elements, and it's because they have similar chemical and physical properties. So periodicity means as you go across the periodic table, a same pattern occurs repeatedly. So for example, if I go across this row, I would go through elements that are highly reactive metals, and then I would go through elements that are not as reactive metals, but still metals. Then I would go through some metalloids, and then some nonmetals, and then a really unreactive nonmetal. If I go down to row 5, I would go through the same pattern. Highly reactive metals, not as reactive metals, some metalloids, some nonmetals, and then some non-reactive nonmetals. Also, notice that the periodic table can be broken up into 4 distinct blocks. We have the S block, which means each of these elements' electron configurations will end on an S. We have the D block, each of these elements' configurations will end on a D, and then we have the P block, each of these ends on a P, and then these are the F block down here. It is no coincidence that we have 2 columns for S, 10 columns for D, 6 columns for P, and 14 columns for F. Also, you should know that the elements in the S and the P blocks are considered representative elements, and that's specified right here, representative elements. So the S and the P blocks are the representative elements. They're also known as the 8 main groups, because notice we have 1, 2, 3, 4, 5, pardon my terrible handwriting, 6, 7, and the 8th group. So these are the 8 main groups. It doesn't mean that these elements in the middle aren't important, but they're not considered part of the main representative elements. The pattern of valence electrons is the last topic of this section, and you'll notice that we have drawn the electron Lewis dot notation for each of these elements. If the element is in group 1, it means they each have 1 valence electron. If elements are in group 2, they each have 2 valence electrons. Skip across the transition metals, and we go to the 3rd group, which is going to be, remember that groups, the S block and the P blocks make up my representative elements. These are from the S block, and these over here are part of the P block. And those are my main group elements. So those are the only ones we're really analyzing as far as pattern of valence. Anything in group 3 has 3 valence. If it's in group 4, it has 4 valence. Group 5 has 5 valence. Group 6 has 6 valence. Group 7 has 7 valence. And group 8 has 8 valence. There's one more element that belongs right here in group 8, but they didn't put it because it doesn't actually have 8 valence electrons. It's helium. Helium only has 2 valence electrons, and yet they place it in group 8 with the other elements that happen to have 8 valence electrons. We'll analyze why that is in the next section. So by looking at the group number on the periodic table, if it's in the one of the 8 main groups, you can tell how many valence an element has simply by the group number that it's located in. The transition elements, which is everything in the D block in this center area right here, these have what's called variable valences, meaning they can have different numbers of valence depending on the situation with their, because they're filling up the D level, and so they could have, shifting in their electrons, which changes their number of valence.